Good day and welcome back for our final installment on triple integrals. At the end of the previous video I mentioned that we are at the point during class I would be passing out a worksheet having you spend a few minutes, probably 30 or so, working on it. You can find this worksheet on Canvas, and if you have not done so already, I recommend spending some time working through the problems and at a minimum kind of sitting them up and getting everything ready to evaluate. What I would like to do in this video is go through the sit-ups of problems 1 and 2, but I'll also note that full solutions are posted on Canvas, giving you all the details that you might need. So in the first problem, we're asked to evaluate a triple integral over some solid E. The solid E is bounded by the surfaces z equals x squared plus y squared, y equals x, y equals 0, x equals 1, and z equals 0. Whew, that's a lot of surfaces. But let's go ahead and just classify these really quick. Z equals the square root of x squared plus y squared is a paraboloid, whereas the following four surfaces are planes. And in fact, the three surfaces y equals x, y equals 0, and x equals 1, we can visualize these, I think, very clearly in the xy plane. And as we will see, those three planes will bound our solid E on the sides, and it will be bounded below by the xy plane, z equals 0, and above by this paraboloid. So if we think about our three planes, we have y equals 0, which corresponds to the x-axis. We have x equals 1, and note I'm only drawing the z equals 0 trace. If you wanted the entire plane, you would just take these blue line segments and drag them up and down parallel to the z-axis. And then y equals x, when we are in this z equals 0 trace, could be represented as a line. And note we very clearly can see a triangular region in the xy plane, which is bounded by those three planes. Now the difficulty is attempting to visualize what the rest of this will look like. We're bounded below by z equals 0, which we can see, and above by this paraboloid. And this is a standard paraboloid opening upward around the z-axis. And we could try to sketch a much more detailed picture of what our solid will look like, but I think we have all of the information that we need. When I'm sketching these, sometimes less can almost be more. Note that we are varying from z equals 0 up until we hit that paraboloid. So in terms of a coordinate system, if you haven't decided already, pause your video and just write down one word here. Do you want to use cylindrical coordinates, Cartesian coordinates, or spherical coordinates? And my suggestion is going to be to use Cartesian coordinates, mainly because of this region of integration we have for the outside double integral. So in terms of this triple integral that we are going to set up, we have an inside integral with respect to z, in Cartesian, so I'm leaving it as xy squared, and then an outside double integral. On the inside, we said you vary from z equals 0 up until you hit that paraboloid, z equals x squared plus y squared, so along this green line segment. In terms of this region of integration, we might think of as D. For that outside double integral, we have a triangular region which is bounded by x equals 1 and y equals x. And we could order these limits of integration however we prefer, but in this case I think it's simpler to put x on the outside, and note x is varying from 0 to 1, and for a value of x between 0 and 1, choose your favorite value. Those corresponding y values vary along vertical lines, going from the bottom curve, y equals 0, to the upper curve, y equals x. And I would suggest that the setup of this problem and being able to sketch the solid and the region of integration for the outside double integral are the most important parts of this problem. Once you get it to this iterated integral, this is something that we should be able to evaluate somewhat efficiently with anywhere from 3 to 5 steps. But of course, you can find those solutions on Canvas. Let me now say something about the second problem as well. We are asked to evaluate the triple integral over e of x cubed plus xy squared, where e is the solid in the first octant that lies beneath the paraboloid z equals 1 minus x squared minus y squared. And this is a very reasonable paraboloid to sketch. It has a vertex on the z-axis at 1, and it opens downward. In fact, we know precisely where this intersects the xy plane. When z is equal to 0, our paraboloid would be 0 equals 1 minus x squared minus y squared, or x squared plus y squared is equal to 1. So if we want to think of a region D in the xy plane, it is bounded by a circle of radius 1. And furthermore, just to maybe give us a hint as to how we would like to set this up, our integrand, both terms contain an x, and if you factor it out, you are left with an x squared plus y squared. And note the convenience. At this point we see that we have a region of integration for an outside double integral, which is circular and symmetric about the origin, and we also see an x squared plus y squared appearing in our integrand. So this would be suggesting that a great approach to this would be to use cylindrical coordinates. So in terms of setting this up, we have an outside double integral over d. On the inside, x would be r cosine theta. X squared plus y squared becomes an r squared. And the dv will become r dz dr d theta. And the z values are going to vary from being z equals 0 all the way up until we hit this paraboloid. And this paraboloid is z equals 1 minus x squared minus y squared, which is 1 minus r squared in polar coordinates. So 0 to 1 minus r squared. And this takes care of the majority of the setup. Of course, you still need to convert this outside double integral into its polar coordinates, but I think that's something that you are all capable of doing. Also note, full solutions can be found on Canvas. I highly recommend going through and finishing these problems and taking a look at the third example. And let me just note, we've used Cartesian coordinates, we've used cylindrical coordinates. I would almost venture to guess what you might want to use for the third example. In our next section, we will begin investigating what we'll call a change of coordinates in double integrals, our version of a U substitution. And when we do this, we will hopefully very clearly see where this extra r came from with cylindrical or polar coordinates. So stay tuned and take care.